In this video, I'm going to continue our discussion on reactions. And so we're going to continue using this chlorination and also bromination in this video as our sort of example here. And so now we want to look at selectivity. And so if we have more than just a methane, if we have a longer hydrocarbon chain than just methane, we want to know which of these carbons is the chlorine actually going to go on, is actually going to bind to. And so I already kind of have the answer up here, is that we see that it's going to select for the secondary carbon here. So we will call this the secondary, which is also often given a 2 prime, and these are primary carbons here. And so it's going to select for that secondary carbon more. And so the reaction that we have going on, we can either have this, so we have one electron going there, one going there, and then the other one going onto that carbon, so that we end up, and I'm just going to put this in the line angle drawing. So we end up with this right here, as well as HCl. Then we bring in another Cl here. And so this will go to there, this will go to there, and this will go on to there to reform our chlorine free radical there. And so we end up then with one of the chlorines bound onto the primary carbon. Where here we are going there, we are going there, and then this one is going down there, so that we end up with this species right here. We bring in our next chlorine here, and so this will bind to that, that will bind to that, and that one will go to there to reform this right there. And so that is the first in the propagation steps right there. Well, this one up here is the first in the propagation step on each of these. So this then was the second propagation step, if you remember from the previous video. And so the thing to notice, though, is that there are more hydrogens on primary carbons than there are on secondary carbons. We have 6 hydrogens, so 3 plus 3, that are bound to primary carbons, and only 2 of them bound to a secondary carbon. And so that's telling us that the hydrogens bound to a secondary carbon must be quite a bit more reactive than the hydrogens bound to a primary carbon. And so we can actually calculate that out here. So if we take these numbers that I have up here, so we end up with 40% of the 1-chloropropane and 60% of the 2-chloropropane. And what I mean by that is you perform this reaction, you'll get your products, and those products will be a mixture of these two species here. And so if you sort of analyze that product, that mixture you now have, 40% of it will be 1-chloropropane and 60% of it will be 2-chloropropane. And so we can calculate the reactivity of each of the 8 hydrogens on propane. So we take that 40% here, divide it by these 6 hydrogens bound to a primary carbon, and we get 6.67% per hydrogen. Then we do that with the 2 on secondary, and we get 30% per hydrogen. We divide those, and we see that the secondary hydrogens are 4.5 times as reactive as primary hydrogens. And so if we look at these reactive intermediates here, we see that the secondary radical is more stable than the primary radical. So we can look at the bond dissociation energy for these. And so this is how much energy you would have to add to break that bond. So you need 397 kilojoules per mole to break the bonds on the secondary carbon to a hydrogen, and you need 410 kilojoules per mole to break the primary carbon to hydrogen bond. And so it takes more energy to break the primary carbon to hydrogen bond than it does the secondary carbon to hydrogen bond. And so in general, as you add more non-hydrogen substituents, so these R groups, onto the carbon, the more stable the reactive intermediate, the more stable the radical is going to be. So the methyl is the least stable, primary is more stable than that, secondary more stable than that, tertiary even more stable than that. And so we can look at the reaction coordinates for these. And so we're going to look at the chlorination and the bromination of these hydrocarbons. And so what we see here is if we are looking at well, this is just the first step, and remember that two-step process of going from the reactant here, this reactant, to having the chlorinated product. So here we're just going to the reactive intermediate as our product. So there would actually be more reaction going on here where this would go even lower than that, where we have our second transition state there. But we're just looking at the first part, so the first propagation step in this chlorination. So the forming of our reactive intermediate, the forming of our radical here. And so what we see is that the activation energy for the 2' here is lower than the activation energy for the 1' here, and it's lower by 4 kilojoules per mole right here. And then we also have that so this is sort of the kinetic look at it. So it's going to be faster on the secondary carbon than it will be on the primary carbon. But we also see thermodynamically that it's more favored on the secondary carbon than it is on the primary carbon by 13 kilojoules right here. And so it's faster because it's lower activation energy, and it's more favorable because we have a lower energy, I don't want to say product, I guess reactive intermediate here. So that is the case for chlorination. What we see for bromination though now is that well, in both cases, whether it's the primary or secondary carbon, they are actually higher in energy than our reactant, at least at this step anyway. Remember, this is just that first step. But we still see that the 2' has the lower activation energy than the 1'. So the primary carbon is going to be higher activation energy than the secondary carbon by 9 kilojoules per mole. And again, the secondary is more energetically or thermodynamically stable than the primary by 13 kilojoules per mole here. So the other thing to notice, and this is called Hammond's postulate, is that when you have an exothermic reaction like this, then the not the intermediate, but the transition state is going to look more like the reactant. So that's what these arrows on top are here for, to sort of show that the sort of the distance, I guess you could say, in kind of the shape, or not shape, but I guess the way that the transition state looks. And so what we see for the chlorination is that the transition state looks more like the reactant, where the chlorine here is less bound to this hydrogen than this carbon is. So this is more bound together than it is to the chlorine. Whereas in bromination, which has this endothermic part of the reaction here, we are actually going to look more like the product of it than the reactant of it. And so this is a shorter distance here than it is to here. So it looks more like the product than it does the reactant. And that is called Hammond's postulate. So we can look at this part of the reaction here. So the chlorination and the bromination. So the thermodynamics of this part of the reaction for chlorination is exothermic, and so for bromination it is endothermic. So the transition state for chlorination is going to look more like the reactants, where for bromination it's going to look more like the products. Then the difference in the activation energy between the primary and secondary carbons here for chlorination is 4 kilojoules per mole, and for bromination it is 9 kilojoules per mole. And so we can actually look at the bond dissociation energies here for it. So we have the bond dissociation energy for forming our HCl bond and forming our HBr bond. Then the bonding dissociation energy for breaking our primary carbon to hydrogen bond and breaking our secondary carbon to hydrogen bond. And so if we just calculate these out, so we're looking at the chlorination of one of the primary carbon and the chlorination of the secondary carbon. We see that the secondary carbon is more negative than the primary, so negative 34 as opposed to negative 21 kilojoules per mole. And so this is going to be more stable or thermodynamically favored. The bromination, we now have both of these as positive because this is endothermic, but we again see that the secondary carbon is lower in energy, and so that is more thermodynamically favored than on the primary carbon. So for both chlorination and bromination, the secondary carbon is going to be more thermodynamically favored than the primary carbon. All right, so now we're going to change gears a little bit. So I've been using this term here, reactive intermediates, of which the radical is one of them. So free radicals are one type of reactive intermediate. So a reactive intermediate is just a short-lived, fast-reacting species. So they do not last long because they react about as quickly as they are formed. And so you're never going to have like, a beaker full of, one of these things here. So the carbocation, the radical, the carbanion, or the carbene, because these are very short-lived species that react extremely fast. And so you'll never have just like a solution of one of these. These things, as we'll see here in a minute, can be stabilized to make them more likely to form, but they're not going to last like significantly any longer in the solution. And so, yeah, these are the 4 reactive intermediates, and we see that these are all on carbon, which, because this is organic chemistry, carbon is sort of the thing we are very interested in. And so that's what we will be talking about here. All right, so for our carbocation here, which is positively charged, it's sp2 hybridized, and we end up with this vacant p orbital here. So this is the sp2 bonds are going to these 3 hydrogens here, and we end up with an unhybridized p orbital that is vacant or empty here. And if we add other things other than hydrogen to it, like this carbon, these have these hybridized orbitals here, and we do get a little overlap here. So we get this sort of inductive effect here, where this is going to help stabilize this p orbital here. And again, I'll probably repeat this multiple times. Stabilizing it isn't going to make it last significantly longer, but it's going to make it more likely to form. So again, you can add a bunch of carbons onto it to help stabilize it, but you're still not going to really get like a solution of these carbocation species. It's just going to make them more likely to form. And so here we can also have stabilization with resonance. So if we have something pull off right here, so say we had like a chlorine right here, and we ended up having the electrons go there, so that it sort of dissociated from this and took the electrons with it, we would then end up with this. So I'll actually draw that over here. So we have this right here, this vinyl group. We have a chlorine bound to it. The electrons go up to there, and so we end up making this. And so now we have this right here, and we can have the electrons move over there, and then we end up with the positive charge on this other carbon here. And so that can help stabilize it and make this reaction more likely to happen. And more likely to happen in comparison to if you don't have that double bond. So if you just had this This is going to be less likely to occur with just this propane than it will with this propene here. And so that resonance stabilization will help make that more likely to happen. Uh, but yeah, so we see here, so sort of speaking of this halogen leaving, we can have this bromine here. We have the electrons go to the bromine, so we form this positive charge. And then we have the inductive effects where these things bound to it here, these carbons here, can sort of donate some of their electron density, so we can have this weak overlap here. And we can see that if we have more carbons, that will help give a little bit more stability to it. So that inductive effect will help stabilize that positive charge. And again, and I'll keep repeating this, you're not going to get a solution full of this stuff, but it is going to make it more likely to form. So if you have this, you're more likely to have this bromine just sort of come off of here, sort of just leave right here. In fact, they call that a leaving group, as we will talk about in future videos. But then we have this, and so something else in the solution is going to come along and try to react with that very quickly. And so something else will react with it. So we will end up with something, well, it will be this. So we have these CH3s on here, and now we have this. So CH2CH3. 3. And so something like this ethanol here will come and quickly react with it. Or you could have water come and quickly react with it, or so on and so forth. The point is, it's a reactive intermediate. And so it's reactive, as I've been saying, and it's intermediate. So it's not going to be sort of a final form of anything. It's going to be in between these different things here. But anyway, that is carbocations. I've been talking already quite a bit about free radicals here, but we'll cover this real quick. So it is sp2 hybridized. We have a single electron in this p orbital here. So that single electron is not part of the hybrid orbital. So it's in this, well, what was a vacant p orbital in our carbocation now has that single electron. And we can have resonance stabilization. So we can have this come down here. We have our sort of single arrowhead like that. This comes here, and then another one goes onto here to end up forming this right here. And again, these are not, this resonance stabilization is not going to make it last like significantly longer in solution. It's just going to be more likely to happen. So if we have, our propane here, and we have this H, which is reacting with our chlorine, this is going to be less likely to happen than if we have this. So then we have our Cl. So this hydrogen is going to come off and become form a free radical more easily than that carbon is. So like if you had a mixture that was 50-50 of these two things and you tried to do this chlorination reaction, you're going to chlorinate with this one a lot more easily than you are with this one because of that resonance stabilization. All right, then we have our carbanion, which looks like this. So this one is actually sp3 hybrid. So this is sp3 hybrid. And so this lone pair is a hybrid orbital. So we have a negative charge, but this lone pair is a hybrid orbital. And that makes sense because this is something that's going to want to bond with something else very quickly. Again, it's a reactive intermediate, so it's going to react very quickly. And so we can actually form this like this. So we have this hydroxide here. It can come and take that hydrogen. Then these electrons will go down there and form our carb anion here. And so what I have shown on here are these bromines, which have the partial negative. So these are more electronegative than our carbon. And so they will actually help stabilize this negative charge by pulling some of that electron density away from the carbon. And so this is, a very important notion in chemistry in general, but organic chemistry in particular here, is that we are trying to stabilize these charges. So charges are not something that like to exist in nature. These things like to try neutralizing themselves. And so if we can pull a little of that negative charge away from that carbon, it will help stabilize it. But again, this is stabilized compared to, so if we just had like a C, a CH like this, so if we just had CHs on here and we put this negative charge on here, this is going to be a lot less stable than this, and so it's going to be a lot less likely to form, which is why we usually don't think of methane as being an acid. So you usually wouldn't think of a hydrogen bound to a methane as being an acidic hydrogen. Uh, and so the more electronegative atoms on here will help stabilize it through these inductive effects. Again, this is not going to be stable by any stretch of the imagination. It's just going to be more stable and so therefore more likely to form. This hydrogen here is going to be slightly more acidic than if these were all just hydrogens bound onto here. And again, we can have this resonance stabilization. So this can go down here, and then we can move that up to there and end up with this species right here. And so we can make these carb anions more likely to form if we have this resonance stabilization. So again, it's that thing where this having a hydrogen or something extracted and becoming this is going to be a lot less likely than if we have this going to this right here. So having that double bond there to help resonance stabilize it is going to make that a lot more likely to occur. All right, then we also have our fourth reactive intermediate here, which is the carbene. And so again, we have a vacant p orbital, but now we have the non-bonding electron pair here in the sp2 orbital here. And so we have both of these electrons in this one orbital here. And so that's in an sp2 orbital right there. There are a few different ways to form a carbene. I'm going to show a couple here. And so there's actually a mistake on here. This hydrogen right here should be a bromine. So that should be a bromine right there. And so I'm going to have this hydroxide come and snatch that hydrogen there. So we end up with the lone pair going onto the carbon. So we now have our carb anion here, just like before. But then we are going to have the electrons from this bond go onto that bromine, which will then leave, and so we end up with this right here. So this is our carbene right here. The other one that I wanted to show is we have this down here. And so this is sort of resonance stabilized. These electrons can go here. Then these ones would go here, and so sort of sharing the negative charge with the nitrogen, which, as we'll see here, is going to be the minor contributor to that, because nitrogens don't like to have negative charge. But that's not really the point of this. What we see here, though, is that these electrons from here will actually go onto that nitrogen right there, and so we end up with our carbene here, and then nitrogen gas. But again, these are reactive intermediates, and they don't like to last very long. And in fact, these things will react with each other. And so probably one of these electron pairs will come and attack this carbon here. And so we end up with this ethene right here. So this double bonded carbon like this. So one of these electron pairs will go to forming the sigma bond, and the other one will go to forming the pi bond on it. So we end up with our double bond on there. All right, so like I said, if we want to look at the sort of stability of these charges on the different atoms, especially these three atoms here, the carbon, nitrogen, and oxygen, that we're going to be using all throughout this video series. And so we want to look at the stabilities of the charges on here. And so for the negative charge, the stability is determined pretty much by the electronegativity periodic trend. So the electronegativity of these atoms. So the further to the right on the periodic table, the better the atom can hold a negative charge. And so I have this here, which shows these electronegativity ratings on here. So carbon is 2.55, nitrogen is 3.04, oxygen is 3.44, fluorine, just for comparative purposes, is 3.98. And so the carbon is going to be the least stable with a negative charge. Nitrogen is going to be a little bit more stable, but nitrogens with negative charges are still extremely unhappy. Oxygens can hold on to a negative charge better than those, and then fluorine, well, in fact, fluorine can hold on to it so well that in our oxygen-rich atmosphere, fluorine would rather be a negatively charged fluoride ion than be a fluorine, than to actually be sort of elemental fluorine. And so the fluoride can actually hold the negative charge quite well. The oxygen can hold it fairly well, nitrogen not very well, and carbon not very well. All right, then when we get to the positive charges though, so now we are just sort of going in the inverse electronegativity periodic trend, but what further stabilizes it will be a full octet. And so that's why you actually see, so the fluorine is going to be the least stable, the carbon is the next least stable, and then you'd think, well, oxygen and nitrogen are more electronegative, and so those must be even less stable than like the carbon, but in fact they are more stable than the carbon. And the reason for that is because they have these full octets. And so we look at the carbocation here. This is missing a bond it wants, and so it only has 2, 4, 6 electrons bound to it when it wants the full octet. It wants the full 8, but it doesn't have that, which makes it a lot less stable. But then the oxygen is less stable than the nitrogen with a positive charge, and the nitrogen is the most stable out of all of them. In fact, if you just put something like ammonia in water, it will extract a lot of hydrogens to become the positively charged ammonium. So that's why nitrogen can act as, I don't want to say a strong base, but stronger than something like water, for instance, because the nitrogen can hold that positive charge better than the oxygen on water. And so it's that full octet thing that makes it so that the carbon, the carbocation, is less stable than even the oxygen cation, which is less, and then it's the periodic trend that sort of takes over from there, and that's why the nitrogen is more stable with a positive charge than the oxygen is. But anyway, that was everything I wanted to talk about in this video. I think the take-home message here is this selectivity for the chlorine on something that has more than just like 2 carbons on it is going to be for these for the carbons with more non-hydrogen things bound to it. So secondary is better than primary, tertiary is better than secondary. And so this trend right here is an important one right here. And so that's kind of a take-home message. The other is that this is because of both kinetic reasons, so the activation energy, and thermodynamic reasons because of the stability of the products, or the stability of the reactive intermediates, to be more accurate. The other one is this Hammond's postulate here that the transition state is closer in its appearance, or closer in its structure, I guess, to the higher energy part here. So with chlorination is closer to the reactants, wherein bromination is closer to these products here. And yeah, that is the take-home message for that part of the video. The take-home message for this one is just that we have these four different intermediates here, reactive intermediates that we're kind of going to be working with. So the carbocation and the carbanion are the two that we're going to be seeing the most. We've been talking quite a bit about radicals in the previous video, just because it's that homolytic cleavage that we can use to get the bond dissociation energies, but the radicals don't figure in as much as the carbocation and the carbanion. And the carbene we will probably work with even less than that. And so, yeah, that is a take-home message from that. The other one is just why these things are more stable, why the fluoride is more stable than the oxide, which is more stable than the nitride, which is more stable than this carbide here. And that's because of this electronegativity trend, and then the positive charge having the stability be based on the inverse of that electronegativity trend, but also based on having a full octet, where we see this carbocation does not have a full octet. Neither does this fluoride ion here, so they don't have that full octet. And the fluoride is extremely electronegative, so that's going to be extremely unstable here. The carbocation being even more unstable than the oxygen or nitrogen because of missing that full octet, than the oxygen being less stable than the nitrogen because of the electronegativity thing. But anyway, I don't want to ramble on too long. I hope you found this video helpful, and I will see you in the next one.